Okay, for my Zoom folks at home, can you hear me? And can you see my screen?
Yes.
Yes, the ball.
All right, and I can hear you. That's good as well. Okay, so let's get the show on the road. Today we are going to be finishing up with C++ inheritance. And we are going to talk about Java interfaces. We're going to talk about how virtual tables or virtual methods get implemented. And we might or might not get to multiple inheritance. If we get to it, fine. If we don't get to it, fine. It's not as important as the other things. Before we start, a couple quick announcements. One, or a couple of reasons I have to take this course online for the next couple of weeks. So course going exclusively online for a couple or several weeks, And I will announce, I'm hoping that sometime in late March, I can bring it back in person. And then the second thing is I've found the office hours I was holding aren't working out as well as I would like. So I'm going to move them. They're going to be Monday 2 to 3 p.m. and Tuesday from 2:45 to 3:45 p.m. I'm finding that it's just, I was hoping I could take a lunch break between this class and Tuesday office hours. It's turning out to be too rushed. And I'm getting to office hours a little bit late. This way, I hold them directly off after class. I won't be late. The same thing Monday, it turns out 11 o'clock in the morning, I did not realize was overlapping with some stuff that normally happens that day. So I'm moving them to 2 to 3. I will post that so that you can all see that. Okay, first thing I want to do is at the end of the lecture last time, I was struggling with showing you something with virtual methods. And so you might remember, did I get rid of it already? Well, looks like I already blew it away. So what I'm going to do is redo it. So I had VI, and I was showing you virtual methods and a quirk in C++ that you need to be careful about. So what I'm going to do is create a virtual method. I'm going to create void draw. I'm just going to say cout. I am in A. Or I am drawing from A. And we'll make it public. And because I did not declare it as virtual, it is final. Now I'm going to create a class B that inherits from A. I'm going to do something you should not do, which is declare virtual void draw. So in effect, I'm saying I'm ignoring the fact that it's supposed to be final up there in A, and I'm going to override it. Now I'm going to create a object x equals new A, and I will print out, I'll draw, and I'll assign it a new B, and I will call draw. And the last thing I'll do is have a B, call it Y. What you're going to see is this is going to call A's draw method. This is going to call A's draw method. But interestingly enough, even though I declared the method to be final in A, and therefore it should be calling A's draw, or A's draw method is going to actually call B's draw method. Let me compile that. Okay, and here is, remember at the end I was struggling because I was trying to compile it. It said can't open the output file for writing for that architecture. Linker failed with exit code 1. This continues the long line of incredibly informative error messages. It turned out foo is a directory, and it won't delete a directory. It would have been so much nicer if it said, I can't open the output file for writing because foo is a directory. So do it into foo1. And there you go. I am drawing from A, I am drawing from A, I am drawing from B. Okay, we'll go back and look what's happening. Okay, when I assign it a and I draw X, because X is an A, it uses this draw method. Okay, now I assign it a B, and again I draw. And the reason it calls A's draw method is because X is declared as A declared draw as final. Therefore, the compiler inserted at compile time a pointer to A's draw method. And therefore, you get, even though you assigned an object of type B to X, it's still calling A's draw method. But this is the anomalous line, is that because Y is declared as B, and because B said, oh, no, I don't care what A said, it's not final, I'm overriding it, and the compiler says, bravo, no problemo, I've got your back, and it compiles it without a peep, not even a warning about the fact that you should not be doing this, and it goes ahead and calls B's draw method. Okay, you should not do this. This is reprehensible. It's an abomination, but I want you to know it exists because the compiler won't even emit a warning message about it. So anyhow, it is what it is, as they say. Okay. Second thing, housekeeping thing I wanted to do before getting to things. Some people have already started working homework 3. I wanted to say a couple things about homework 3. The most important, it's all about problem 5, where you're essentially writing a number of classes for graphical objects. So just a couple things about number 5. First of all, it says you should define 3 enumerated constants for an arc side labeled as small, medium, as large. That means you should use Java's enumerated types. Okay, it doesn't mean you should use like int const or final int small equals 10, final int medium equals 20. It means I want you to use Java's enumerated constants for that. The other thing that you need to know for graphical interfaces is that the y-axis is not where you think it would be. So you are asked to implement a contains point method. And let's say that it's 10, 100. So this is X and this is Y. And let's say you have a rectangle whose top is 50 and whose height is 100. You would think if you are going by a normal way of doing things, you'd say, okay, that means this is 0, this is out toward infinity, this is out toward infinity. So what I must have is a rectangle whose top is 50, and it must come down here to minus 50 because that's its height. And therefore, this point cannot, this y value cannot lie in there, and you'd say false. But that's not how graphical packages draw. On Windows systems, the y-axis is inverted. And in fact, 0 is there, and it goes down like that to infinity on the y-axis. So in fact, when I say that a rectangle has a top of 50, it actually starts here and goes to 150, meaning that this point is actually in the rectangle. As long as, let's say that the left was 0 and the width was, say, 200. Okay, so the rectangle would essentially go like this. And the point is like right there. So it does fall in it. So that takes some getting used to. So the bottom line is that when you're drawing or graphical packages, all graphical packages assume that the y-axis starts at the top of the window. Not the bottom. So you have to get used to that. If you're wondering why, it's an artifact of the fact that when you used to have displays, the way the electron guns, they'd have electron guns and they'd run left to right, top to bottom. Therefore, it was more convenient to specify Y as the top, being at the top of the window rather than the bottom. So it's a historical artifact. And you just got to deal with it.
I have a question about homework 3.
Okay. Yes. Oh, by the way, okay, just before, but it also makes sense. If like here's a terminal window, okay, where is the stuff at the terminal window? It's actually here at the top, right? So again, even the way windows are organized are kind of, and now I can make it bigger by extending it down. So in fact, even the way you interact with windows is of a way that Y is at the top. Okay, another question about homework 3.
For the draw methods, are we simply calling methods from the graphics package,
Yes.
or do we need to implement them? Because when I was looking at the API.
No. So
Okay.
yes, you're delegating. So the question is, for the draw methods, are we simply calling the draw methods from the graphics object? And the answer is absolutely yes. You're delegating your calls to the graphics object.
Okay.
There's no way that you could spend the entire week trying to figure out what are the algorithms for actually drawing these things. Meaning how you draw it bit by bit. So yes, absolutely delegate the call to the draw methods in the graphics object. So right here, you're being passed a graphics object. If you go and look at the API for this, so if you just do a Google search for graphics, Java, top search, and it doesn't matter. We're using SE8, but SE7 is just as good. And if you go down in the API, you'll see things like draw a line, draw oval, draw a polygon. Those will draw the boundary. And if you want a fill, then you call fill rect, fill round rect. So just so you know, if you say draw, it will draw a transparent rectangle with just the boundary. If you want it filled with a color, you have to call fill rect. And if you want the, don't think I require this, but if you want a boundary to appear, it actually, a drawing order has to be fill. And then the order of calls has to be this way. And the reason is that if you have a thick boundary, say it's 5 pixels, then 2 pixels will slop into the fill area. And if you do the order draw rect and then fill rect will overwrite 2 of those pixels. The innermost 2 pixels, it will overwrite and it'll look like the border is only 3 pixels wide. So the order that you draw is important. You first call fill and then you call draw. Now I think I don't require you to draw a boundary for this homework assignment, so that may not come into play, but okay. Does that answer the question?
It does, thank you.
Okay. So in that case, let's move on and talk about, I think we finished where we're going to talk about constructors in C++. So first of all, you have the constructors. I'm not going to go into details because you should know them, but constructors that initialize an object. This is C++. Then you have a copy constructor. Okay. That gets called when you pass a object by value to a function or return an object from a function or initialize a object with another object. That is, if you say, if you have something like stack S, and then you say stack Z equals S, or you say stack Z of S. These are initialization statements that call the copy constructor. Copy constructors don't exist in Java because you cannot pass by value. You can only pass by reference. If you want to copy, there is a clone method that you override in Java. So in Java, should you want a copy, a deep copy of an object, there is a method called clone. You override that. An object, the object class, defines a clone method. Okay, I'm not going to talk about copy constructors. I assume you know what copy constructors are. I just want it clear that Java does not have copy constructors. It has a clone method that will create a deep copy. Similarly, C++ has an assignment operator. Again, because that works for stack allocated objects. And Java does not have stack allocated objects, therefore Java does not have an assignment operator overloaded. If you do assignment in Java, so in Java, if you have stack S and Z, and if you say that Z equals S, that means Z gets a pointer to S. That means when you're done, this is a stack. It means that both S and Z point to the same stack. You do this in C++. In C++, it does a deep copy. So in C++, this equal operator will copy contents of S to a new stack and assign that stack to Z. But that's because C++ supports stack allocated objects and Java does not. Okay, so all I'm really going to care about, for the most part, is our regular constructors that create new objects. And you may or may not have been introduced to initialization lists. So in Java, so first of all, in newer versions of C++, you are allowed to initialize things like age equals 5. I forget which version. I think it's C++11 lets you do it, but C++98 does not let you do this. So it's always dangerous to use initialization statements like this in C++ because if someone has an old compiler, this doesn't work. Okay, so generally in C++, the way that you perform initialization is with what are called initialization statements. So if you have a, let's say, int a or age, what you'd normally do when you created a constructor for person is you would use what's called an initialization list. So if you haven't seen these before, it's important that you know about them. The initialization list is a comma-separated list of assignments of values to instance variables, and they are executed before any statements in the constructor body. This is where if you need to call a superclass constructor, you call the superclass constructor. So for example, if person, let's say we, person extends employee. I know it'd normally be the other way around, but you would put the call to the superclass constructor here. in the initialization list. And you can see that unlike Java, you give the name of the base class. In Java, you would have used super to call the constructor. In C++, you give the name of the base class. The reason is C++ supports multiple inheritance. You can actually inherit from multiple base classes, which would make super ambiguous in some cases. So the way they handle that is you give the name of the constructor you're calling. Now, you should use initialization lists to assign things because it saves time. And I have a program to show you why that is so. So let me bring up that program. I think it's this one. Yes. Okay. So what I'm doing is I create a class X, and it has a single instance variable called val. Now I have a 0 argument constructor that sets val to 0, and you can see I have it called X's 0 argument constructor. I have a 1 argument constructor that uses an initialization list and says this is X's 1 argument constructor is called. I have the assignment operator that assigns a value from v.val to v. So if you're assigning another X object to this X object, you copy the contents of that object. And finally, I have a copy constructor that assigns the value from the copy into X. Okay, so that's X. Now I have a class Y that has an object of type X. And the first thing I'm showing you is what happens if I assign value to T in the initialization list. If I do that, what happens is it will call the copy constructor. It will copy the contents of copy the contents of val into T. So down here, I create an X object with the value 3, then I create a Y thing and pass in this X to it. Okay, so what I'm going to do is create a new window. I'm going to compile this, run it. So what happens is when I declare value to be 3, that's where X's 1 argument constructor gets called. Then when I create val and assign it and pass value as a argument, it calls X's copy constructor. So this right here is calling X's copy constructor. Okay, now what I'm going to do is change it up. And I'm going to not use an initialization list. And instead, I'm going to do what I see a lot of people do, which is simply assign val to T. Okay. I'll compile it. And look what happens. So this is the same. The 1 argument constructor gets called when I create val. But this is what happens when I use assignment. So you may understand this one. Obviously, that's what's happening here. That's the assignment operator getting called. So the question is, what is this? Okay, what that is that when I declare T to be of type X, it has to be initialized. Before I go into the constructor, it has to be initialized. So what happens is, since I didn't provide an initialization list telling the C++ compiler how to initialize T, it says, I'm going to look for a 0 argument constructor for X, and one exists. There is a 0 argument constructor for X, so it goes ahead and it calls it. So when you don't use an initialization list, what happens is you end up with 2 method calls rather than 1, which makes your code less efficient. Okay, so the bottom line is all objects do get initialized before you enter the function body. The question is, do you control destiny by saying how that initialization is done, or do you not control destiny by not providing an initialization list and letting the C++ compiler do it for you, and then you waste a second call with the assignment? So that is why you're supposed to use initialization lists. It really doesn't matter for primitive types like integers, floats, booleans, chars. I think that's it. But it matters for any object, especially strings. Okay, so any rate, that is why you use initialization lists in C++. Okay. So we went over last time how to declare subclasses. We went over virtual versus non-virtual methods. Okay. If, let's say that we had a draw method here. Let's say that we have class fruit. This is C++. And we have a draw method. And we make it virtual because we want it to be overridable. And it does some stuff. And now we have class orange. And it inherits. It's a subclass of fruit. And let's say that it wants to override draw. And let's say the first thing it wants to do is call fruit's draw method. The way it does it, it calls fruit, prefixing double colon, draw. So in Java, it would be super.draw. In C++, it is the name of the base class you want to call : draw. Another thing in C++, at any time, I could leave this virtual off. And once I leave virtual off, it becomes final. So any subclass of orange should no longer be able to modify draw. Of course, we know it can. Same thing is true in Java. At any time, I'm allowed to declare a method final. And thereafter, any subclass cannot override it. So I can stop the virtualness anywhere that I want. Okay.
Dr. Vanderzen,
Yep, go ahead.
would you care to open up that play directory you were in so we can look at the example programs you had?
Oh, make it, unfortunately, it's on my local computer. I can try to post these files.
Oh, that would be wonderful.
Yep.
Thank you.
Yep, unfortunately, this play space is on my laptop, so I'll try to post them to Piazza. Okay.
So
Okay. Do you want an email as a reminder for that, sir?
Yes, actually, if you could email me that, I would appreciate it.
I'll do that.
So a superclass could have a virtual method, and at any point in the hierarchy, a subtype could say, okay, this is final, and then all subtypes of that subtype would default to that method?
Yes, exactly. You got it exactly right. So at any point in the subclass hierarchy, you can make it, you can turn a virtual method and make it final. And
Okay.
below that point, it is final. So if I now make class naval be a subclass of orange, naval supposedly should not be able to override draw anymore. Okay. Now, last thing, order of constructor calls, which is the same for both Java and C++. So I have another program, and I'll post this one too. So I am going to create a class fruit and a constructor fruit that counts I am a fruit. Then I create a class orange. So I'm going to show the order in which constructors get called. So class orange is now of type fruit, and you can see it has a constructor. And now I create a naval orange, which is, and see out I am a naval orange. Okay, and actually, yep. Okay, so now in main, I declare a naval where I pass in an argument and a naval where I don't pass in an argument. Actually, I'm going to change it so I'm a naval 1 arg constructor. I am a naval 0 arg constructor. Here I am orange 1 arg constructor. Whoops, but it's not, it's a 0 arg. And okay, so basically I have a inheritance hierarchy where what I have done is created a fruit. Orange is a subclass of fruit. Naval is a subclass of orange. And what I want to show you is when I create a naval orange, what's going to happen is the naval constructor automatically calls the orange constructor, which then calls the fruit constructor, and they keep calling until you get to the top of the hierarchy. So the order in which things are going to execute is going to be the fruit constructor, then the orange constructor, and finally the naval constructor. And that ensures that by the time you execute the naval constructor, all necessary initialization has been done by its superclasses for their instance variables. Okay, so all I'm doing is proving to you that in fact, the order of execution of constructors goes from the top to the bottom of the inheritance hierarchy. And this is true of Java too. It makes sense that you want each parent class to initialize its own objects. Okay, so the first one was a declaration of naval with a 1 argument. So you can see the first thing that executes is I am fruit, then the orange 1 argument constructor, and finally the naval 1 argument constructor. Same thing, when I declared the naval with a 0 argument, the first thing that happened is it called fruit, then the 1 argument, the 0 argument orange constructor, and then the 0 argument naval constructor. Okay, just again to go back. So first I created a naval with a single argument, then I created a naval with no arguments. But bottom line is in both Java and in C++, constructors get called top to bottom. And that is the same for the copy constructor too. Mhm. This was in main. And then this was calling fruit. And fruit had only a 0 argument constructor. There was no, orange and navel both had a 0 and 1 argument constructor. Fruit only had a 0 argument constructor. So this got executed. Fruits got executed first, then orange's 1 argument constructor. Okay. Okay, so I think we have pretty much taken care of constructor stuff in C++. Okay, and just as a reminder, when you declare something to be a subclass, like when I say class orange, I need to be careful to declare public what it's inheriting from. Because if I forget that, then anything, let's say that I forget it, that means that anything that was public in fruit becomes private. So that's not what we want. So if I forget the public declaration, then any public method in fruit will become a private method in orange, and that's not what you want generally. But remember, I went over composition, and if you do in C++ want to inherit implementation but not the interface, you can say protected fruit. And that will make the methods from fruit be protected, and you will still inherit their implementation. Okay. Now, that takes care of C++ inheritance. What I want to move on to is Java interfaces. So Java decided that they wanted to be able to define pure abstract types. So this is an abstract type in Java. And the way you declare it is interface, and then some number of method declarations. And then any number of, well, you can intermix them, but normally then any number of constant declarations. So for example, you would be allowed to say int pi, well, that's not a good example, double pi equals 3.14, whatever you want. So interfaces are completely devoid of implementation. They can only be a declaration. So for example, I might say interface list, or actually let's do a stack. I'd say interface stack, and I might say, might have a method for pop. So I might have int, this would be an int stack pop void push int value, maybe int peak or top, Boolean is empty. Okay, so this would be an example interface for methods. Now, generally, you want the methods to be public, and in order to make that happen, you declare the interface as public. That means then everything in that interface is considered public. We will get to how you can create so-called template interfaces that support. This is obviously not ideal because stacks, you'd like them to be able to support strings or any object, and you can't do that just yet. But when we get to generics, we will talk about how you can change the interface so it can support an arbitrary type. So you can do that. You can also extend an interface. So for example, in the map, you have, in the collections, you have a map interface. And then you have a sorted map. So you can say then public sorted map. Now you would say extends map. And then you could add additional methods. So this sorted map is a subtype of map. And you might add methods for traversing that map in sorted order, for example, or doing a range query over the map. Okay, so again, in Java, try to remember you need to declare them typically public, your interfaces. You just, it's like a .h declaration in C++. Just method signatures, prototypes, and then any constants you want. Now, more recent releases of Java have introduced the notion of default methods, but that is primarily to address a problem whereby, let's say you create an interface and a whole bunch of code is based on that interface, and later you decide you want to add an additional method to the interface. Then the problem is every class that implements that interface would have to implement the new method, and that could be problematic. And so Java realized that was a maintenance nightmare, and they decided to add the notion of default methods, which are only supposed to be added to an existing interface. They're not supposed to be created from scratch, meaning when you create the interface initially, you're not supposed to use default methods. And it's too advanced for this course. So when I say that interfaces are devoid of implementation, I'm telling a white lie. Okay, but for this course, the lie holds. They are devoid of implementation. Now, so I now can create concrete classes that implement the interface. So for example, I might have class array stack, and it uses the implements keyword to indicate that it's implementing the stack interface. And you can actually implement as many interfaces as you want. You would simply give a comma-separated list. Okay, so for example, in addition to implementing stack, maybe it wants to also implement a serializable interface so that it can be written out as a byte stream to some file system. So in that case, you would have it implement two interfaces. Once you say that you implement an interface, you agree to implement all methods in the interface. at the same protection level or at the same access level. So normally that is public. Normally interfaces are public, therefore you would agree to implement all methods as public. Okay, the other thing you get is you may now use any constant from that interface. So for example, remember how I had the constant pi. The way that Java envisioned having global constants, so sometimes you want global constants. Why would you want to always have to come up with a value for pi or Planck's constant in a chemistry program? The way they figured you would do that is you would define an interface of global constants, and then you would just have classes implement that interface, and they'd be able to access all those global constants. The other way that you can do it, which is I think the way Java typically does it, is it simply makes public the class variables in certain classes. So there's like a math class perhaps, and it would just have math.py, math dot. So I think the way that Java actually does it is to define classes, and they have static final variables that they make public. And that tends to, I've never actually seen someone use an interface to create a set of global constants, but I've read that that's how they intended it to be. The big important thing with interfaces that trips up a lot of people is that even though they are an abstract type, you're allowed to declare a variable to be of that type. So stack is a interface type and is devoid of implementation, yet I can say S equals new array stack. And now I can use any of the methods that I defined for a stack. So I can say s.push 20, s.push 50. Let's say system.out.println s.pop. So as long as I assign an instance of a concrete class to that interface, even though this is an interface, that's okay. Because as long as that variable points to a class that implements that interface, we're good. Okay. So you can assign, basic bottom line is you can assign to an interface variable an instance of any class that implements that interface. The API for that interface. Okay, so this is how you create an abstract type in Java. And then, so when you're designing things, you sometimes have to distinguish between whether you're going to have an abstract type or an abstract base class. The reason for having an abstract base class is that typically you want to declare some variables, some properties, and some default methods. So generally, if you're trying to make up your mind, okay, do I declare an interface for an abstract class? Here's a couple considerations. Okay, one, you can provide default methods or default implementations in an abstract class. And it may have instance variables. Okay, so but as against that, a class may implement multiple interfaces, but may inherit from only one class. So it's great if you make both a stack and a serializable abstract base classes, but when you make an array stack, you can only inherit from one of them, and now you're stuck because you can't get anything from the other one now. So that's what argues often in favor of declaring something to be an interface, because that is, you're allowed to implement multiple interfaces. And that way, depending on the situation, you look like a different type. So when I have back here, array stack implements stack and serializable, I can actually have, let's say, array stack A equals new array stack. And now I can say stack X equals A, but I can also say serializable Y equals A. So depending on the circumstance, I can make A look either like a stack or I can make it look like a serializable object, depending on what I want to do with it. If I want to write it to a file system, I'll make it look like a serializable object. If I want to push and pop stuff onto it, I'll make it look like a stack. So that's the advantage of declaring interfaces, is that then when you have a class implement that interface, you can make it look like that type, but you give it the freedom to also act like another type. Okay, so this is Java's way of implementing multiple inheritance. So interfaces are Java's way of implementing multiple inheritance. And you're like, wait a minute, inheritance is supposed to be implementation of implementation, but it's not. The way the programming language community understands inheritance, it is the inheritance of API. With implementation a side benefit. The programming community views composition as the appropriate way to inherit implementation. So when you hear people say, Java doesn't support multiple inheritance, what they're really griping about is you can't inherit implementation from two classes in Java. But those people are not, I know I'm being pedantic here, but those people aren't also using inheritance in the way that it's commonly understood, which is that inheritance means that you are inheriting an API. It's a type. Okay, I think the last thing for today is how do we implement virtual methods? Okay, how to implement So how's the compiler do it, is the question. How does the compiler? Okay, so basically the compiler has to leave until runtime the decision as to what draw method to call. If you have, say, a graphical object, and I have gDraw, and that's a virtual method, then draw will depend, the draw method that's called will depend on what object, type of object G points to, like rectangle, oval, image. So the way it's done is with something called a vtable. Stands for virtual table, our original. Okay, so it uses a vtable. Okay, so what happens is every object, if it has virtual methods, at location 0, there is a pointer to something called the vtable. The vtable is an object. So let's say this is a rectangle. Its first 4 bytes is a pointer to a vtable. At location 0 might be a pointer to the draw method. And at location 4 might be contains point. And that points somewhere to an address. So what happens is no matter what, every graphical object will have the draw method at location 0. Every graphical object will have contains point at location 4. So what happens is when you define a graphical object and you make draw and contains point virtual, it assigns them locations in the vtable. Now remember I said is visible. I made it be non-virtual. It is not assigned a location in the vtable because since it's not virtual, the compiler can assign it a address at compile time because all subclasses of graphical object will call the same version of is visible. So it's not in the vtable. Now let's say that rectangle adds a couple other methods like get color and makes it virtual for some reason. It starts filling in the vtable below where graphical object did. So now it would put get color as the third one. So basically your superclass defines the first part of the vtable for you, and then you fill it, you can add to the vtable, but after the superclass. So that means for every subclass, the draw method is in the same place, the contains point is in the same place. So essentially, all the compiler does is emit a set of assembly language instructions that looks like this. So the first thing it does, if it has a method call of the form fm, first it loads the address of f into a register, which it needs no matter what, because it's got to pass the this pointer to m. So the address of f is going to become the this pointer. Then the V table is always at location 0, so you can immediately get the contents of the V table and stuff that into another register. And then you know the offset, you know what position in the V table M is. So let's say it's at index location 2 and our pointers are 4 bytes. Then R2 plus 8 will give you the address of M in the V table, and the star gives you its actual address that you should jump to, and then call star R2 to jump. Okay, so it is pretty easy implementation wise. It does create some efficiency issues because so this instruction is always required in order to get the this pointer, but these two instructions are not required if the method is non-virtual. If it's non-virtual, the compiler can simply essentially do a direct call to a fixed memory address. So anytime you have a call to a virtual method, those two additional instructions have to get executed, and access to the V table, and then you have to pull the address out of the V table to jump to. But this isn't what actually really slows things down. This isn't horrible, unless your method is only 1 or 2 lines long, in which case this really does add overhead. But if your method is pretty involved, this isn't what makes it so bad. The issue is that if the compiler does not know at compile time what method it is calling, it's hard to optimize stuff. So for example, one thing that compilers like to do is they like to inline very short functions. If I have, like for a rectangle, if I have a function getColor, okay, and all it does is return, say, C. What compilers like to do is inline that. If you have something like A equals R.getColor, a smart compiler will just translate that to R equals R.C, essentially. And that's called inlining. It's basically throwing away the function. Okay, inlining the function. Okay, basically code for the function replaces the function call. Much like expanding a macro. Okay, that increases efficiency by eliminating the function call. And then the compiler can do other things knowing what that code is. But if it's a virtual method, it has no idea what method will get called, so it can't do this inlining, plus any other optimizations it can get once it has inlined it. Okay, now hotspot compilers get around this problem. What they'll do is figure out, okay, 80% of the time, it's a call to a rectangle. 19% of the time, it's a call to a text object, and 1% is something else. And so a hotspot compiler will basically start saying like, okay, if obj equals rectangle, then A equals R dot C, else if obj equals text, then A equals text is get color function. Else, go ahead and call R dot get color. So a hotspot compiler will start figuring out, are there certain objects that predominate here? And we'll start basically putting in conditional checks that allow it to do inlining and make stuff more efficient. Okay, so last thing, that same thing that works for V tables works for the rest of it as well. So the remaining fields would be first anything from graphical object, instance variables. Then it would be rectangles. Added instance variables. So the same mapping for the instance variables. The superclass goes first, then the added variables after that. And the same thing, now, no matter what, if there's a visible, if you define visible in graphical object as like Boolean visible, then, and you have graphical object X equals new rectangle, and you say something like V equals X dot visible, the compiler at runtime or at compile time knows exactly where that address is. It's going to be, say, at location maybe 4 in the V table, no matter what the object is, whether it's a rectangle, whether it's an oval, whether it's a line, the visible slot, the visible property will be at offset 4, and it can put that code in there. So that is the magic secret sauce behind how both Java and C++ in general, any compiler is going to implement virtual methods. And also why virtual methods slow things down. It's not so much that virtual methods slow things down because they add 2 instructions, which they do, but because they prevent inlining and all the optimizations that can come from being able to inline. Okay, so that wraps up inheritance. Don't worry, the one thing I don't care about for this class is multiple inheritance in C++. I do care about mix-in inheritance, which is called composition, but you don't need to worry about multiple inheritance. So we're finished inheritance. On next Tuesday, we're going to move into module mechanisms. It will be a blast because we're going to blow through C, C++, and Java in one day. And then later next week, we'll start into generic functions, which is essentially how do you write templates in C++ and in Java. Okay, so I will see you all on Tuesday. Remember, it will be virtual. I apologize for that. And I will see you then.
Are you not going to take questions, sir?
Yes.